Hello all. In today's lecture, we will discuss the inverse of that transform. Because the purpose of that transformation is often to simplify the solution of time domain problems, it is essential to inverse transform that transform functions to time domain. We have systems in discrete time, and we need to return to the time domain by the inverse that transform. For system modeling, Z transform functions are used. For interpretation by human, time domain functions are used. We have two simple approaches for inverse Z transformation. The first is long division, and the second is partial fraction expansion. And we have two cases for partial fraction. The first case is simple real roots, and the second case is complex conjugate roots and real roots. First, we will use the long division to obtain as many terms as desired of the Z transform expansion. We use the coefficients of the expansion to write the time series. We will see the two steps used to give the inverse Z transform of function f of z. First, we use long division for expansion of f of z to get f naught, f1 z power negative 1 until fi z power negative I. This is the summation of k equals 0 to I fk z power negative k. We write the inverse transform as the series or the sequence f naught, f1, fi, and so on and so forth. The number of terms I obtained by the long division is selected to yield a sufficient number of points in the time sequence. We need sufficient points in time sequence. Let's see an example. Obtain the inverse Z transform of the function f of z equals z plus 1 divided by z squared plus 0.2z plus 0.1. First, we will divide z plus 1 by z squared plus 0.2z plus 0.1. We divide the first term, which is z, divided by z squared, we get z power negative 1. Then we multiply z power negative 1 by z squared plus 0.2z plus 0.1. We get z plus 0.2 plus 0.1 z power negative 1. Then we subtract z plus 1 minus all these. Then z minus z equals 0. 1 minus 0.2 equals 0.8. 0 minus 0.1 z power negative 1 equals 0.1 negative 0.1 z power negative 1. Then we divide the first term by the first term here, which is z squared. 0.8 divided by z squared, we get plus 0.8 z power negative 2 here. Then we multiply 0.8 z power negative 2 by this, the denominator. We get 0.8 plus 0.16 z power negative 1 plus 0.08 z power negative 2. Then we subtract minus, minus, and minus. 0.8 minus 0.8 equals 0. Negative 0.1 minus 0.16, negative 0.26 z power negative 1 minus 0.08 z power negative 2. Then we divide this by z squared. We get negative 0.26 z power negative 3. Then we multiply it by z squared, and so on and so forth. We will use only the first three terms, which is the first one is 0, then z power negative 1, then 0.8 z power negative 2, then negative 0.26 z power negative 3. The inverse transformation, we have the time series or the sequence 0, 1. We take the coefficients of z, 0.8, then negative 0.26. Note the decreasing coefficient denotes that the system is stable. We have the coefficients are decreasing, then the system is stable. The second method is partial fractions. This is identical to using the inverse Laplace transform. The same method was used in inverse Laplace transform. The most that functions have the term z in their numerator, it's often convenient to expand f of z over z rather than f of z. To get the z in the numerator for f of z, we expand for f of z divided by z. Let's see an example. And before it, the partial fraction expansion allows us to write the function as the sum of simpler functions that are the z transforms of non-discrete time functions. The procedure for inverse z transform is first we find the partial fractions of f of z divided by z over f of z. Then we obtain the inverse f of k using the z transform table we have seen in the last lecture. Let's see an example. Case 1, simple real root. We have z plus 1 divided by z squared plus 0.3z plus 0.02. We factorize the denominator to z plus 0.1 times z plus 0.2. Then we divide both sides by z. We get f of z divided by z equals z plus 1 divided by z times z squared plus 0.3z plus 0.02. We have three partial fractions, a over z, b over z plus 0.1, and c divided by z plus 0.2. To get a, we substitute by z equals 0 in the fraction z plus 1 divided by z plus 0.1 times z plus 0.2. As we cover dz, or we multiply all the function by z. We can multiply all this function by z, then z in the denominator is cancelled with the z multiplied. We get z plus 1 divided by z plus 0.1 times z plus 0.2, and we substitute at z equals 0. We have 1 divided by 0.1 times 0.2, or 1 divided by 0.02 equals 50, then a equals 50. To get b, we multiply all the function to the left by z plus 0.1, the denominator of the second partial fraction. Then this is cancelled with this. We have z plus 1 divided by z times z plus 0.2. We substitute by z equals negative 0.1. We have 1 minus 0.1 divided by negative 0.1 times negative 0.1 plus 0.2. Then we have b equals negative 90. To get c, we multiply the fraction or the function to the left, f of z divided by z, by the denominator of the third partial fraction, which is z plus 0.2. Then z plus 0.2 is cancelled with z plus 0.2. We have z plus 1 divided by z times z plus 0.1, and we substitute at z equals negative 0.2. Then we have 1 minus 0.2 divided by negative 0.2 times negative 0.2 plus 0.1, which is equal to 40. Then we have the three partial fractions. We multiply each by z. We get 50 times z over z, negative 90 times z over z plus 0.1, and 40z divided by z plus 0.2. The first term is 50. We get from the table of the z transform, the first term is 50 times delta of k, or impulse of k, and 490z over z plus 0.1, which is 90, and this is in the form of a to the power k. We have a equals negative 0.1, then negative 0.1 power k, and for the third term is 40, and z divided by z plus 0.2 is in the form of a power k, which is negative 0.2 power k, for k bigger than 0, and 0 for any k smaller than 0. Note that f of 0, if we substitute by 0, negative 0.1 power 0 equal 1, negative 0.2 power 0 equal 1, then we have 50 minus 90 plus 40 equals 0. We can have the time sequence rewritten as, we can shift, or we say negative 90 times negative 0.1 power k plus 40 times negative 0.2 power k for any k bigger than 1, and 0 for any k smaller than 1. We will see the same example, but we will not divide by z. We now have f of z equals z plus 1 divided by z squared plus 0.3z plus 0.02. We factorize the denominator to z plus 1 plus 0.1, I'm sorry, times z plus 0.2. Then we have two partial fractions, a divided by z plus 0.1 and b divided by z plus 0.2. To get a, we multiply the left-hand side or the function by z plus 0.1, which is cancelled with z plus 0.1. We have z plus 1 divided by z plus 0.2, and we substitute with z equals negative 0.1. We have 0.9 divided by 0.1, which is equal to 9. Then a equals to 9. And for b, for the second partial fraction, we multiply the function by z plus 0.2. Then z plus 0.2 is cancelled with z plus 0.2. We have z plus 1 divided by z plus 0.1. We substitute at z equals negative 0.2. We have negative 0.2 plus 1 divided by negative 0.2 plus 0.1. We have 0.8 divided by negative 0.1, which is equal to negative 8. Then f of z equals 9 divided by z plus 0.1 minus 8 divided by z plus 0.2. From the table, we multiply and divide by z each term, 9z divided by z plus 0.1 and negative 8z divided by 0.2, z plus 0.2 times z power negative 1. The first one is 9 times negative 0.1 power k, and multiplication by z power negative 1, we have a shift by negative 1, which is k minus 1. And also for the second term, negative 8, and this is in the form of 0.2 power k, but we have multiplied by z power negative 1, then we have a delay by negative 1 for k bigger than 1 and 0 otherwise for k smaller than 1. We want to get f of z using f of z divided by z and f of 0 not equal to 0. We have f of 0 equals 0, f of 1 equals 1, and f of 2 equals 0.7, f of 3 equals negative 0.23, and f of 4 equals 0.055. This is valid, however, f of 0 equals 0 or f of 0 not equal to 0. Without division by z, we have the function negative 0.9 times 0.1 power k minus 1 plus 0.8 plus 8 times negative 0.2 divided power k minus 1. If we substitute by k equals 1, then we have f of 1 equals negative 50, and f of 2 equals 1, f of 3 equals 0.7, f of 4 equals negative 0.23, and f of 5 equals 0.055. This is valid only in case of f of 0 equals 0. Here we have the function f of z by z, and f of 0 equals 0, 50 minus 90 power, times negative 0.1 power k, plus 40 times negative 0.2 power k. We have the same sequence, negative 50, 1.7, negative 0.23, and 0.055. The first one is okay, and second one is not okay. Another example, find the inverse z transform of f of z equals z divided by z plus 0.1 times z plus 0.2 times z plus 0.3. We have three partial fractions, a divided by z plus 0.1, b divided by z plus 0.2, and c divided by z plus 0.3. To obtain a, we multiply the fraction by z plus 0.1, and we cancel both z plus 0.1 in the numerator by z plus 0.1 in the denominator. Then we substitute by z equals negative 0.1. We have 1 divided by negative 0.1 plus 0.2 times negative 0.1 plus 0.3. I'm sorry, this is 0.3. We get a equals 50. And for the value of b, we multiply the left-hand side by z plus 0.2 and cancel z plus 0.2 with z plus 0.2 and substitute by z equals negative 0.2. We will get 1 divided by negative 0.2 plus 0.1 times negative 0.2 plus 0.3, which is equal to 100. Then we get the third coefficient, which is c. We multiply the equation to the left by z plus 0.3. Then we cancel z plus 0.3 with z plus 0.3. We have 1 divided by z plus 0.1 times z plus 0.2 and substitute at z equals negative 0.3. We have 1 divided by negative 0.3 plus 0.1 times negative 0.3 times 0.2, which is equal to 50. Then we substitute by each of them. We multiply by z. We get 50 times z divided by z plus 0.1, negative 100 z time divided by z plus 0.2, and the third term, which is 50 z time divided by z plus 0.3. We get the coefficients, or the inverse, z, which is 50 times negative 0.1 power k, negative 100 times negative 0.2 power k, and 50 times negative 0.3 power k for k bigger than or equal 0 and 0 otherwise, for k smaller than 0. Now we have the second case, which is complex conjugate roots and rare roots. If we obtain the partial expansion, we use residues method shown in case 1 with complex conjugate pools. We obtain the partial fraction expansion a times z divided by z minus lp, which is the pool, and a star, which is the conjugate of a times z divided by z minus p conjugate. We have two conjugate pools. We have theta p and theta a. Theta p is the angle of the pool, and theta a is the angle of the pool fraction coefficient. I'm sorry, the angle of the partial fraction coefficient a. We have theta p, which is the angle of the pool p, and theta a, which is the angle of the partial fraction coefficient a, respectively. We use the exponential expression for cosine function to obtain f of k equals 2 times the magnitude of a, which is the partial fraction coefficient a magnitude, and the magnitude of p power k times the cosine theta of the pool times k plus theta of the coefficient or partial fraction coefficient a. Now we will find the inverse z transform of this function as an example. z cube divided by 2z square plus 1. I'm sorry, z cube plus 2z square plus 1 divided by z minus 0.1 times z square plus z plus 0.5. We have here three partial fractions, which is a1 divided by z and a2 divided by z minus 0.1 as we divide both sides by z, and a3 divided by z plus 0.5 minus j 0.5, and a3 star divided by z plus 0.5 plus j 0.5. For the first coefficient a1, we multiply both sides by z. Then z is cancelled with z. We get z cubed plus 2z squared plus 1 divided by z minus 0.1 times z squared plus z plus 0.5. We substitute at z equals 0. Then we have 1 divided by negative 0.1 times 0.5, which is equal to negative 20. To get a2, this is a2, which is called b. We multiply both sides by the denominator of a2, which is z minus 0.1. We multiply, then this term is cancelled with z minus 0.1. We have z cubed plus 2z squared plus 1 divided by z times z squared plus z plus 0.5. Then we substitute at z equals 0.1. We get 0.1 cubed plus 2 times 0.1 plus 1 divided by 0.1 times 0.1 squared plus 0.1 plus 0.5, which is equal to 19.689. For the third coefficient, we multiply both sides by the denominator of a3. This is cancelled with z plus 0.5 minus j 0.5. We have z cubed plus 2z squared divided by z times z minus 0.1 times z plus 0.5 plus j 0.5. And substitute by z equals negative 0.5 plus j 0.5. Then we get a equals, or a3 equals negative 0.5 plus j 0.5. And for a3 conjugate, we will only change the sign of the complex part, then it will be 0.656 minus j 2.213. Then we will have negative 20, 19.689 times z divided by z minus 0.1, and the two fractions a3 divided by z plus 0.5 minus j 0.5, and the a3 conjugate times z divided by z plus 0.5 plus j 0.5. We convert a3 from the rectangular form to the polar form, which is equal to 2.308 e power j 1.283, which is the angle theta a in radians. And for the pole, we have to get the pole in the polar form, negative 0.5 plus j 0.5, then it will be equal to 0.707 e power negative j 0.785, which is the angle in radians. For the first term is negative 20 times delta of k, and for the second term here equals 19.689 times 0.1 power k, and for the third term we will have 2 times the magnitude of a times the magnitude of the pole power k times the cosine theta of the pole times k plus theta of the coefficient a, or the partial fraction coefficient a. Find the inverse z transform of the following function. This is given as report. Now we will see the relation between E of Z and E star of S. E star of S is the sampled form of E of S. We have E of S, then we have a sampler, then we got E star of S. The Z transform of a sequence E of k is defined as Laplace of E of k equals E of z equals E of 0 plus E of t times z power negative 1 plus E of 2t times z power negative 2 and so on and so forth. The standard transform of a time function E of t, E star of s equals E of 0 plus E of t times E power negative ts plus E power of t 2t times E power negative 2ts and so on and so forth. And we have from the definition of the Z transform E power ts equals z. Then E of z equals E star of s at E power ts equals z. We have E of z equals E star of s at E of ts, E power ts equals z. Now we will see the pulse transfer function and manipulation of block diagrams. Pulse transfer function is a ratio of the Z transform of the sampled output and input at the sampling instance. Now we will derive the expression for the Z transform of this system. We have E of S, then a sampler, we get E star of S, then the block diagram of the system, then we have the output Y, then a sampler, we get Y star of S. We first start at Y of S equals E star of S times G. Then we have the sampler here to get Y star. We sample E star of S times G of S. Then we get E star of S times G star of S. Then Y of Z equals E of Z. E star of S is equal to E of Z at E power TS equals Z. And G star of S equals G of Z. Another example, we have E of S, then a sampler, E star of S, then a block diagram G1, G2, Y of S, then sampler Y star of S. We will get Y of S equals G1, G2 times E star of S, or E star of S times G1, G2. Then we get Y sampled. We get E of S, E star of S times G1, G2 all star. We get E star of S, and then we multiply G1 by G2 and get the star value of it. G1, G2 is all star of S. Then we have Y of Z equals E of Z times G1, G2 of Z. Then we have G1, G2 of Z, which is not equal to the Z transform of G1 times G2, or it is not equal to G1 of Z times G2 of Z. We multiply G1 by G2 of Z, then we get the output Y as E star times the multiplication. This is not equal to G1 of Z times G2 of Z. We multiply G1 by G2 of Z. Now we have an example. If we have G1 of S equals 1 over S and G2 of S equals A divided by S plus A, then the Z transform of G1 of S times G2 of S equals the Z transform of the multiplication of these two functions, which is A divided by S times S plus A. We first take the partial fractions or obtain the partial fractions A over S plus B over S plus A. Then we will get 1, A equals 1 and B equals negative 1, 1 over S minus 1 over S plus A. Then we get the inverse inverse Laplace transform, 1 over S, which is having the time function equal 1, and 1 over S plus A equals e power negative AT with a negative sign. Then we get the sampled form of it, which is G1 of KT times G2 of KT, which is 1 minus e power negative AKT. Then we get the Z transform of the multiplication, which is equal to Z transform of 1 equals Z divided by Z minus 1. And for the exponential is Z divided by Z minus e power negative AT. we get the common denominator, z minus 1 times z minus e power negative 8e, and for the numerator, we have z times 1 minus e power negative 8e. Then y over e of z equals z minus, times 1 minus e power negative 8e divided by z minus 1 times z minus e power negative 8e. Another example. An open loop sample data system is presented. Derive an expression for the transform of the output of the system, which is y star. First, we get y as a function of x star, which is equal to g2 times x star. And for x is equal to e star of s times g1. And x star equals the star of x of s, which is e star times g1 star. Then we get y equals x star times g2. We substitute x star. We get y star equal x star times g2 star. We substitute by x star, which is equal to e star times g1 star times g2 star equals y star. We substitute y star by y of z. Then y of z equals e of z, g1 of z, g2 of z. For an example, we get g1 equals 1 over s and g2 equals a divided by s plus a. We get the z transform of the first one, which is z divided by z minus 1. And for the second term, we get the z transform of g of s, which is equal to a times z divided by z minus e power negative at. Then we get y divided by the e, which is equal to az squared divided by z minus 1 times z minus e power negative at. We multiply g1 of z times g2 of z. Note, from example 2, we have g1 times g2, and for the example number 3, we have g1 of z multiplied by g2 of z, which is equal to az squared divided by z minus 1 times z minus e power negative 80. Now we will find the time response. We have the open loop time response of sample data system can be obtained by finding the inverse Z transform of the output function. A unit step signal is applied to an RC circuit as shown in figure, which is an R and a capacitor circuit 1 over SC, and this is R, and this is V input, and this is V output. We need to draw the output response of the system assuming a sampling time equals 1 and RC equals 1. We have here U, then sampler, U star, G, the transfer function, then Y, then a sampler, then Y star of S. The function for the RC circuit equals S 1 divided by S plus 1. We have the output here equals 1 over SC divided 1 plus R divided by SC. Then we multiply SC in the denominator. We have SC plus 1. SC plus R. And we have the term added to the S equals 1, or we have to make it all 1. Then we have G of S equals 1 divided by S plus 1. First of all, we get Y, which is equal to G times U star, or U star times G. Then we have the sampler. We have U star times G star. Then Y of Z equal U of Z times G of Z. For the unit step, we have U equals Z over Z minus 1, which is the input. We got the transform of the unit step, which is the input. and multiplied by the z transform is its function, which is equal to z divided by z minus e power negative at or e power negative t. We multiply those by each other, z divided by z minus 1 times z divided by z minus e power negative t. We get z squared divided by z minus, minus 1 times z minus e power negative t. We substitute by s time equals 1 second and e power negative 1 equals 0.368. We have z squared divided by z minus 1 times z minus 0.368. The output response can be obtained by finding the inverse z transform of y using partial fractions. We get y of z divided by z, which is equal to a divided by z minus 1 minus b divided by z minus 0.368. We get a and b. A equals 1.582 divided by z minus 1, and 4b equals negative 0.582 divided by z minus 0.368. Then we multiply both sides by z. We have 1.58 times z divided by z minus 1 and negative 0.582 times z divided by z minus 0.368. We get the inverse z of this, which is 1.582 times unit step minus 0.582 times 0.368 power k. We substitute by k equals 0, we get y of 0 equal 1, and by k equals 1, y of 1 equal 1.367, and y of 2 equals 1.503, and y of 3 equals 1.552, and y4 equal 1.571. We have the samples at 0, t, 2t, 3t, and 4t. Then the first one is an impulse, 1.367 impulse shifted by time t, 0.503 impulse shifted by 2t, and 1.552 impulse shifted by 3t, and the last one is 1.571 times the impulse shifted by 4t. Or we can drop the t and delta of k, delta of k minus 1, delta of k minus 2, delta of k minus 3, and delta of k minus 4. Now we will see the modeling of zero order hold. The impulse response of zero order hold is a unit pulse with width t. We have a unit pulse with a width t from kt to k plus 1t. The pulse can be represented by a positive step at 0 time, followed by a negative step at time t. We can represent it by a positive step at time t, followed by a negative step at time t minus t, or shifted by time t. This is a digital to analog converter, modeling of digital to analog converter as zero order hold. We have the Laplace of the unit step equals 1 divided by s, and for a unit step shifted by time t, we have e power negative ts divided by s. Then the Laplace of u of t minus u of t minus t capital equals the Laplace equals 1 over s minus e power negative ts divided by s. We have s as a common. We have 1 minus e power negative ts divided by s. Digital to analog converter, analog system subsystem, and analog to digital converter combination transfer function. We have a zero order hold, which is represented by a pulse of width t, then an analog subsystem, then a sampler, then we have the output. For the zero order hold, or the transfer function of the digital to analog converter and analog subsystem cascaded, is g of s times g of the zero order hold, which is 1 minus e power negative ts divided by s times g of s. Now we will see example number 5. Assume that the example of 4 is used with a zero order hold. We have a zero order hold in the system. What will the system output response if a unit step input is applied and if a unit ramp is applied? We have G1 equals 1 minus e power negative ts divided by s, which is the transfer function of the zero order hold. And for the RC circuit equals 1 over s plus 1. We have y equals G1 U sample times G1 G2. We need to get the sampling of this function. Y sampled equals U sampled times G1 G2 sampled of S. Then we have Y of Z equals U of Z times G1 G2 of Z. G1 G2 of S equals 1 minus e power negative ts divided by S multiplied by S 1 over S plus 1. Then we have 1 minus e power negative ts times 1 over S minus 1 over S plus 1. Then G of Z equals, this is equal to 1 minus Z power negative 1, 1 over S equals Z over Z minus 1, and 1 over S plus 1 equals Z divided by e power negative 1, which is equal to 0.632 divided by Z minus 0.368. For the input unit step, we have U of Z equals Z divided by Z minus 1. Then Y of Z will multiply the transfer function by the U, which is equal to 0.362 times Z divided by Z minus 1 times Z minus 0.368. Using the partial fraction method, we write Y of Z divided by Z equals A divided by Z minus 1, the first partial fraction, and the second partial fraction is B divided by Z minus 3.368. We have A equals 1 and B equals negative 1. Then we multiply Z at the right side, at both sides. Then Z divided by Z minus 1 and negative Z divided by Z minus 0.36. We have unit step minus 0.368 power K. We substitute by K equals 0. We get 0, and by K equal 1.63, K equal 2, we get 0.86, and K equal 3, then 0.95, and then K equal 4 equals 0.98. We can write it as an impulse, then 0.63 impulse K minus 1, 0.86 impulse K minus 2, 0.95 impulse K minus 3, 0.98 impulse K minus 4. For the unit ramp, we have U of Z equals Z divided by Z minus 1 squared. We multiply U times the transfer function, which is equal to 0.632 Z divided by Z minus 1 squared times Z minus 0.368. We multiply the denominator. Then we use the long division to get the terms. 0.63 Z power negative 2, 1.5 Z power negative 3, 2.45 Z power negative 4, 3.43 Z power negative 5, and so on and so forth. Then 0.63 impulse of K minus 2, 1.5 impulse K minus 3, 2.45 impulse K minus 4, 3.43 impulse K minus 5, and so on. Then we have these values 0.63, 1.5 at the third sample, and 2.45 at the fourth sample. We have another example. The open loop diagram of the system has a gain of 1 over S plus 10, and the sampling time is 0.1. Derive an expression for the Z transform of the output of the system in case of without zero order hold and with zero order hold. We get G of T, which is e power negative 10t. Then the G of Z equals Z divided by Z minus e power negative 10t. We have t equals 0.1. We substitute by 0.1. We get Z divided by Z minus e power negative 1, or Z divided by 0.3678. Without zero order hold, we multiply the G of S by the G of the zero order hold, which is 1 minus e power negative st divided by S. We have 1 minus e power negative st times 1 over S times s plus 10, we get the partial fractions of this, which is a over s plus b over s plus 10. We get a equals 0.1 and b equals negative 0.1. We have 1 minus e power negative st times 0.1 over s minus 0.1 over s plus 10. Then we have this value, 0.1 as a common factor, 1 minus e power negative st times 1 over s minus 1 over s plus 1. Then 0.1, 1 minus z power negative 1, 1 over s, which is equal to z divided by z plus minus 0.1, and 1 over s plus 10, which is equal to z divided by z minus e power negative 10t. We substitute by t equal 0.1. We have 0.1 z minus 1 divided by z minus 1 minus z minus 1 divided by z minus e power negative 1. We have 0.1, and this is 1, minus z minus 1 divided by z minus 0.3678. Then we get the common denominator, z minus e power negative 1 minus z plus 1. We get z is cancelled with negative z. We have 0.1 times 1 minus e power negative 1 divided by z minus 0.3678. Then g total of z equals 0.06321 2 divided by z minus 0.3678. Then without and zero order hold, we have g of s equal g of z, equals z divided by z minus 0.367, and with zero order hold, we get g of z equals 0.063212 divided by z minus 0.3678. For switching frequency equals 10 Hz and sampling response at t equals 0.1, we have the system with analog system, which is the curve in blue, and for the discrete signal without zero order hold, with zero order hold in red, we can see that the output response is more accurate with zero order hold. It tracks the analog signal, and for the discrete signal without zero order hold, it is away from the original or the analog signal. If we increase the frequency and decrease the step time, we have a more accurate with increasing the switching frequency. The curve in blue is the analog signal, and for the curve in red is the discrete signal with zero order hold, and the discrete signal without zero order hold is in black. We see also that for the system without zero order hold is not accurate as that with a zero order hold. We have this example as a report. G1 is zero order hold, and G2 equals 1 over S times S plus 1. We have Y equals U star times G1, G2, and then we proceed by the steps. Open loop block diagram of a system with zero order hold as shown in figure 6.26. Calculate and plot the system response when a step input is applied. The input U of the system is a unit step, assuming that the sampling time equals 1 second. Now we have finished this lecture. See you in the next lecture.